A quick review of all of our derivative rules and formulas. So you should try these first on the worksheet and then come back and check your answers. So we know the derivative of a constant is 0. In number 2, we've got the power rule. So we're going to bring down the exponent. So 2 times negative 7. And then we reduce the exponent. And you can rewrite that with x to the 8th in the denominator if you wish. And in number 3, 2 to the negative 7th is a constant. There's no variable here. So the derivative of a constant is 0. In number 4, the derivative of sine is cosine. And in 5, the derivative of cosine is the opposite of sine. And in number 6, the derivative of tangent is secant squared. And if you forgot that, you could, of course, start by writing tangent as sine over cosine. And then you could do the quotient rule. But hopefully you don't want to take time during a quiz or a test to do that. I'm just going to go backwards here instead of scrolling each time here. So the derivative of cotangent, when it starts with a co, we know the derivative is going to be negative. So the derivative of cotangent is negative cosecant squared x. The derivative of secant is secant times tangent. And the derivative of cosecant, likewise, when it starts with a co, remember that its derivative will be negative. So we'll have negative cosecant x cotangent x. And again, if you forgot, you would write cosecant as 1 over sine x, and then you could do the derivative using the quotient rule. So that's where these formulas come from. All right, inverse sine, our derivative is 1 over the square root of 1 minus x squared. Remember that when this is not a x, when it becomes a function of x or a glob of x's, then you'd have to add a chain rule. The derivative of arc cosine or inverse cosine is the same, but it's negative. And the derivative of inverse tangent is 1 over 1 plus x squared. So again, none of these are requiring the chain rule yet. These are just our basic formulas. Our favorite derivative, the derivative of e to the x, is e to the x. The derivative of 2 to the x is 2 to the x times the natural log of the base. Let me, again, to save some scrolling here, let me go out of order. The derivative of e to a glob of x's is e to that glob with a chain rule on the glob. So I'm going to bring the 7 in front. 17, don't get fooled by this one again. There's no variable. This is a constant. The derivative of a constant is 0. All right, let's go back and pick up 15. The derivative of the natural log of x is 1 over x. And you can see why we can't have x, or given that x is greater than 0, remember that natural log is only defined for positive values of x. The derivative of the natural log of the absolute value of x is exactly the same. And again, notice that we have to avoid 0 in the denominator here. So the natural log of the absolute value looks like this, and then we are finding out that its derivative is the reciprocal function. So the derivative, this is what f prime would look like. So if you're curious about comparing f of x and f prime of x. All right, so let's do the next section in order. We still have one more log problem here. The derivative of the log of x in base 7 is 1 over x times the natural log of the base. Where this comes from is the change of base formula. If you had written f of x as, I want that to be natural log of x over natural log of 7, and then do the quotient rule. That's how you would come up with this formula. 20 is our quotient rule. So we want the denominator squared, and then we want up here low d high, the derivative of the numerator is just 3, minus the high function times the derivative of the low function. So again, high d low minus low d high. Oops, I said that wrong. Low d high minus high d low. And we could clean that up a little bit. Notice here we're going to have a 6x, and here we have a minus 6x. So all that we will have left in the numerator here is a negative 21 over our denominator squared, so you should add that one extra step. 21 is asking you to write the quotient rule. So exactly what we just did a minute ago. So we have the denominator function squared, and then let me give myself some more room to write here. So now let me say this correctly. We want low function d high minus the high function times the derivative of the low function. All right, let's see what else we've got here. Product rule in number 22. So for the product rule, we're going to take the first function as it is times the derivative of the second plus the second function, leave it the way it is, times the derivative of the first function. This is a power rule, so negative x to the negative 2. And you could rewrite this. You could put these in the denominator if you wish. You could get a common denominator. So these are both going to be negative terms here, so you could put the negative in front. So this term is a cosine x over an x, and the second term is a sine x over an x squared. You could get a common denominator, but it's not going to serve a big purpose, so I think either of those forms are fine. In 23, we're asked to write the product rule. So exactly what we did in 22. The first function times the derivative of the second plus the second function times the derivative of the first. 24 is maybe one that's easy to forget. We've got a variable in the base and in the exponent. So what we need to do is take ln of both sides first. So let's rewrite this. I'm not doing a derivative. I'm just writing natural log of both sides. And the reason we need to do this logarithmic differentiation is because our property of logarithms, the log of a power is the power times the log. So that's the only way we can get that variable out of the exponent. So now we have natural log of y times x natural log of x. And now we can do the derivative of each side. So here we have 1 over y. And on the right side, we need to do the product rule. So the first glob is an x and the second is ln of x. So we'll have the first term x times the derivative of natural log plus natural log of x times the derivative of the first x is just 1. So these x's cancel. Oh, and here terrible, let me back up. Natural log of y, derivative, what did I do? I forgot the chain rule. Hopefully you would have caught that mistake since I didn't end up with a derivative. So one more step here then. If I solve this for y prime, I'm going to move the y to the other side. So I'm going to move the y, and then we have a 1 plus ln of x. And even better would be, since we can replace, we know that y is x to the x. So That might be even one step better to get our answer back in terms of x. All right, now we start doing some chain rule problems. All right, so in 25, we've got a glob, a function inside the tangent function. So it's a composite function. The quadratic function is nested inside the tangent function. So here is our chain rule in action. So we do the derivative of the outer function. So the derivative of tangent is secant squared. And we leave the inner function alone. And then we do a chain rule on that inner function. And that chain rule requires power rule of 10x. So it would be logical to put that 10x in front. But again, the form of your answer is not important here. In 26, I see the composite of three functions. I have a linear function inside of a cosine function inside of a power function. That's the 1/2 power. So we've got to do the chain rule repeatedly here. So the first thing, I'm going to think of this square root as the 1/2 power. So I'm going to keep the cosine of 5x plus 3 and reduce this power. So all I've done is the power rule. Leave the inner function alone. Now I'm ready to do the next chain rule. So the next inner function is cosine. Let me scroll again for some space. So now the derivative of cosine is negative sine. And I leave that linear function alone. And then I have to do that one more chain rule. And that's to do the derivative of the 5x plus 3 term. And that would just be a 5. So you might, I think this would be easier to write if we move the negative out in front, and then we've got 5 halves, and the sine term is in the numerator. This we might move to the denominator since we have a denominator anyway. And again, you don't have to move negative exponents to the denominator, but you might choose to do that. So there's the negative 1/2 power. All right. Arctangent, and now we have a chain rule here. So remember that this term 7 over x, we're going to think of this as 7x to the negative 1 when we do our chain rule. So our formula for the derivative of arctan is 1 plus the glob squared, and then a chain rule on the inner function. So the chain rule here is a power rule. So negative 7x to the negative 2. So let's think how we can rewrite this function. I'm forgetting about the negative 7 here. Let's put the 7 in the numerator, and this x squared, x to the negative 2 is x squared in the denominator. And you don't have to show this step. You might go right to the next step. Notice what happens when we distribute. So I think our best answer here is going to look like x squared plus 49 in the denominator. So when it's obvious that you can remove the complex fraction, remember we don't like to have fractions inside the denominator. All right. 28 is our very definition or rule for chain rule. This is a composite function when one function is nested inside another. So what we've been doing with the chain rule, we do the derivative of the outer function, we leave the inner function alone, and then we do the chain rule on the inner function. So that you should recognize as the chain rule. 29, I have x's and y's mixed together. So remember that this is implicit differentiation. And remember that every time that you see y is really a function of x. So remember that y requires a chain rule when we do the derivative to find y prime. So this first term right here requires a product rule. So we think of this as two functions multiplied together. So the product rule, I'm going to take the first term x times the derivative of y would be 1 with a chain rule on the y, so that would be a y prime. Every time you differentiate a y, remember to tack on that y prime. So first times the derivative of the second plus the second part y times the derivative of x would just be 1. So there's our product rule. And then our derivative of 3y squared is 6y to the first power. And then every time we differentiate y, remember that we need to do a chain rule. In the right-hand side, we have a power rule. The derivative of 7 would be 0. All right, so this y term should move to the other side since it does not have a y prime. And then these two terms are going to remain on the left side. And I'm going to right away factor out that y prime. And I hope you would skip this step and go right to the next step, but to make sure that we don't lose anybody. So now the reason for factoring out that y prime is so that we can get a formula for slope. So remember what y prime is. Y prime is the slope of any tangent line. So if I know any point, if I know a point xy on that function, x1, y1, I just plug it into the x and the y to find the slope of the tangent. So don't forget that derivatives, no matter how we do the derivative, we're always finding the slope of a tangent line at a point. All right, we're almost there. Here we've got a product rule that requires a chain rule inside, and then a bunch of terms will be part of our GCF. So this I'm thinking of as our first function and this as our second. So our product rule says take the first function as it is and multiply by the derivative of the second part. So I'm going to do a power rule, bring the 3 down in front, reduce the exponent to a 2, and then don't forget that we've got a chain rule here. The chain rule on this inner glob, I should say the chain rule on the entire binomial is just 3 because the derivative of the 2 is 0. All right, and then the second part of our product rule, we keep the second part as it is, and we multiply by the derivative of the first part, and that requires a power rule. So reduce the exponent to a 4, and then a chain rule on the inner binomial would be a 6x to the 5th. Okay, so this is really a binomial right now, so let's inspect the two parts here and notice that the GCF, they both have a 3 in common. They both have an x to the 6 plus 1 to the 4th power in common. And both terms have a 3x plus 2 to the 2nd power. So this is our GCF that comes out in front. So what's left from the first term would be one of the 3's and a binomial x to the 6 plus 1. From our second part, we've taken out a 3, so we'd have a 5 times a 2. So we'll have a 10 as our coefficient, a 10x to the 5th as our coefficient. And then we also have a 3x plus 2 factor. Okay, so this will, hopefully you'll remember doing problems like this one previously in class. So why we factored that GCF is because now the distributive property here is going to give us some like terms. So our first term in the here is 3x to the 6th, and in this one we have a 30x to the 6th. So combine the two like terms. And then we're going to have a 20x to the 5th, and back here we've got a 3 from the first part. Okay, so cleaning that up took more work actually than the product rule did. And one more. Here I see a function that I do not want to expand, so I would definitely do this with a chain rule. So the outer function is a fifth power. So I'm going to do a power rule, and I'm going to leave everything inside just the way it was. So a power rule first, and now I've got to do a chain rule on what's inside these square brackets. So the derivative of what's inside, I would do a power rule on this first parenthesis, and the derivative of the -1 is just 0. So the derivative of this -1 doesn't have an impact. But now we still have one more inner function. Notice we still have this x squared inside, so we've got one more chain rule to go. So the derivative of the x squared minus 1 is a 2x. So if we clean this up, 5 times 5 times 2. So let's put a 50x out in front, and then we'll just leave this term. We don't want to expand this. That answer is as good as we can get it.